Hi, this is TW Huang. Today we are going to understand how to program static task graph parallelism in Taskflow. This is the takeaway for today's presentation. We are going to learn how to program static task graph parallelism in Taskflow and understand some of the important design philosophy behind Taskflow. Then, I will showcase a real-world application of static task graph programming and conclude the talk. Static task graph programming, or STGP, is the most basic programming model in Taskflow. It is based on a construct and run model. You define the task graph first, and then submit it to the executor for execution. Let's take a look at an STGP example. Suppose you want to do four things, A, B, C, and D. Each represents a function or a task. A runs before B and C, and D runs after B and C. To get a parallel execution for this task graph using STGP, you have to define a task flow and an executor first. Then, you define four tasks in terms of C++ lambda function objects, A, B, C, and D, and use the precede and succeed method to relay the dependencies among A, B, C, and D. When the graph is constructed, you submit it to the executor for execution. As you can see from this example, you define the task graph first and then submit it to the executor for execution. That is the definition of STGP. A task in Taskflow is a callable object. Basically, it can be anything for which the operation stood invoke is applicable, such as lambda expression, functor, function pointer, bind expression, and so on and so forth. There are two major methods in Taskflow for you to create a task: placeholder and in place. The placeholder member function creates a placeholder task whose work can be assigned later, while the in place member function creates a task with work assigned immediately upon creation. In this example, task A is a placeholder and does not have any callable assigned to run yet, while task B will run the assigned callable which output its identity. Notice that a placeholder task is a valid task, and it actually occupies a node in a task graph. Soon after its creation, you can use it right away to build dependencies with other tasks. Each time you create a task, Taskflow will create a node in the graph and return a task handle of type tftask to you. This handle is a copy chip wrapper over the node pointer to the task in the Taskflow. It provides a set of methods for you to access and modify the task attributes, such as building dependencies, assigning a name, changing the word, querying the statistics, and so on. For example, here I use the handle of task A to assign a name, build a dependency to task B, query its number of successors and predecessors, and assign a work to replace the placeholder with a callable. This slide shows you how to traverse a Taskflow graph using its member function for each task that applies a unary function to each task. At the body of this unary function, I print the name of the task and then apply another two unary functions to traverse all successors and predecessors of that task using its member function for each successor and for each predecessor. So, if you have a task graph like this, you will see this output: four tasks, and the successors and the predecessors of each task. After you define a task graph, you can submit it to the executor for execution. A TF executor manages a set of worker threads to run submitted tasks. The core scheduler implements a work stealing algorithm to achieve dynamic load balancing, as well as a notification algorithm that can adapt worker availability to dynamically generated task parallelism. Execution methods are either blocking or non-blocking. Blocking methods will wait for all tasks to finish before returning, while non-blocking methods will return immediately. You can use the run method to submit a task flow for execution, whether to run it once, multiple times, or repeatedly until the given condition is met, and so on and so forth. When you submit a task flow for execution, you will get a TF future object, which is basically derived from standard future, with a few Taskflow specific operations such as cancellation added. Then you can use the future.wait to block until that Taskflow finishes or executive wait for all to block until all submitted tasks finish. You can visualize a Taskflow by dumping it to a dot format through a C++ output stream using the member function dump. For example, here I dump the Taskflow through the standard output stream and paste the dot output to the online visualizer such as GraphViz Online to visualize the Taskflow graph. Visualization is super important because it helps you understand how tasks and dependencies are structured, making it easier to analyze and debug your Taskflow programs. Now, we are going to understand some important design philosophy behind Taskflow. A key aspect of Taskflow is we do not touch data abstraction. This is a very important decision that we have made during the early stage design of Taskflow. Taskflow is designed to focus on task parallelism rather than data parallelism. Specifically, Taskflow is not a data parallel programming model like Dataflow, which often targets fine-grained parallelism, but rather a task-based model which targets coarse-grained parallelism. More importantly, Taskflow is not designing yet another data abstraction for you to do parallel programming. And that is because the way your data should be optimized for your parallelism is completely depending on your applications, which apparently we don't know too much about. Then, how do I communicate data among different tasks? There are two approaches. First, you can capture your data directly in a Lambda when creating a task. This is simple and works pretty well if the data is available at the task creation time. Second, you can attach your data to a task using the C-style pointer void star that can be set and accessed through the member function data of a task handle. Most applications can be realized by static task graph programming because many parallel workloads exhibit static behavior with a fixed dependency structure. There's no recursion, parallelism is flat and happens only in the first hierarchy of the graph. There's no control flow either. The execution flow of the graph is acyclic and predictable. That brings the following advantages of STGP. Programming models are very simple, and it is very easy to reason about the task graph. Code complexity typically grows linearly with the graph size. More importantly, since the graph structure is known upfront before the execution, we have the smallest scheduling overhead and a better opportunity for compile time optimization. On the downside, the biggest problem of STGP is that the graph structure must be known before execution, either at the programming time or runtime. As a result, you do not have the flexibility to dynamically assemble different task graphs driven by runtime variables or control flow result. Another key aspect of Taskflow is the lifetime of a task. Every task belongs to a graph at a time and remains alive with that graph. That is, as long as a Taskflow remains alive, all of its associated tasks remain alive. Understanding the lifetime of a task is very important because it affects the callable, particularly the captured values. When the Taskflow is destroyed, all of its tasks and their captured variables are also destroyed. For example, the code on the lower left can crash because the Taskflow is destroyed after the block, while the executor is still running it. So, it is always your responsibility to keep relevant task flows alive during their execution. Now, I'm going to showcase a real-world application of static task graph programming. We have successfully applied Taskflow to parallelize an important application in VLSI design, the Static Timing Analysis application, or STA. Static timing analysis is a key step in electronic design automation, or EDA, to validate the expected timing behaviors of the circuit. Basically, STA wants to find out what signals cannot arrive on time. A typical STA algorithm consists of the following steps. First, it derives a timing graph from the given circuit and induces timing constraint from sequential elements like a flip-flop. Then, it propagates timing quantities such as slew, delay, arrival time, and required arrival time from inputs of the circuit to the outputs of the circuit. When all quantities are evaluated, we validate data path and identify any violations. Most STA algorithms require us to propagate timing values from the input of the circuit to its output, and the computation is typically very irregular. For a given circuit, we use Taskflow to derive a timing propagation task graph, where each task represents per pin propagation function and each edge represents pin-to-pin dependency. Then, we run the Taskflow to evaluate and report violated data path in parallel. We have implemented this task parallel propagation in an open source library called OpenTimer v2, while version 1 v1 was implemented using OpenMP to carry out the widely used levelization-based or loop parallel timing propagation algorithm. We levelize the timing graph and apply loop parallel timing propagation level by level. From these results, we can clearly see the advantage of task parallel timing propagation algorithm. Regardless of the number of CPU cores we use, there is always a consistent gap between task parallel and loop parallel timing propagation algorithms. And that is because task parallelism allows us to more asynchronously parallelize the timing propagation without the need of level-by-level synchronization. This slide shows an example implementation of our algorithm in OpenTimer v2 that implemented the forward and backward timing propagation algorithm using Taskflow. In the core function build prop task, we traverse the timing graph to build a Taskflow graph, where each task encapsulates different propagation functions such as RC timing update, slew update, delay update, arrival time update, and so on and so forth. And each edge represents a task dependency between two propagation tasks. We do this for both forward and backward timing propagation algorithms. As you can see, the core propagation function is fully parallelized using just static task graph programming. The resulting parallel code is very concise thanks to the expressiveness of Taskflow. In today's presentation, we have learned static task graph programming in Taskflow and understood some important design philosophy behind Taskflow. We have also seen a real-world application of static task graph programming, where we use Taskflow to successfully parallelize a VLSI static timing analysis application. If you are interested in learning more about Taskflow, please check out our project website at taskflow.github.io. You can post your questions on the issue page of our GitHub repository. With that, I'm going to stop here. Thank you very much.